Uh, can everybody see my screen?
Yes.
Yeah.
All right. So, hi guys. Welcome to Recitation 11, I think, for Gans, Generative Adversarial Networks. Uh, our aim in this recitation, at least for the first half, my aim would be to give you an intuitive understanding of how GANs work and how we train GANs. And we'll look at a vanilla implementation of GANs. In the second half, Kushal will go into more detail of different kinds of GANs and uh, look under the hood, what kind of problems we face while training GANs. And I think next week in the regular lectures, we'll take a deeper look into GANs and see how look at the math and actually different varieties of GANs. And uh, yeah, so with that, we'll get started. So GANs, I mean, I'm pretty sure a lot of you've heard about GANs. They have been quite popular. Deepfakes especially have uh, taken over a lot of things. You must have seen a lot of videos of fake videos of people speaking things that they would never speak, and that all comes. All of that is possible with GANs, and I mean this is a quote from Jan LeCun who says that GANs and adversarial training in general in machine learning has been the most interesting idea in the last 10 years in ML. So to start looking, before we start looking at GANs, I'd like to uh, show you a video of what GANs can do. Pretty sure most of you would have seen some video like this, and a lot of the applications of GANs are kind of controversial. People are making fake videos of other people, and kind of controversial in the sense it could be used for good and bad. But here I'd like to show you, a a way in which GANs can be used to help or do good rather than just uh, you know make fake videos of people. So can you hear me? So can somebody let me know if they can hear the audio of this video?
Yep.
Malaria isn't just any disease.
Is the audio audible? Like, can you hear the video?
Yeah. I mean, I'm able to hear.
Malaria isn't just any disease. It's the deadliest disease there's ever been.
Se dice que ha matado más de la mitad de la población que ha existido. وما زالت تقتل طفلا كل دقيقتين. Mais nous pouvons y mettre fin. Nous savons comment, nous en avons la possibilité. Ameora di karbai ki zarurate.
我们需要让世界领导人关注。Hivyo tunazindua kampeni ya sauti. Omwele bawarupi malaria.
Speak up and say, malaria must die. One voice can be powerful, but all of our voices together, then they will have to listen. Malaria must.
So yeah, this was one example of GANs where this was again generated using deep fakes, and Beckham was obviously not speaking in all those languages. Other people recorded those portions of the audio, which was then like Beckham was speaking them, it seemed like, and his lips were also moving as if he was speaking those languages. But of course, he wasn't. And all this and things like this are possible with GANs, and it has various applications in CGI as well, and is also can be used to make fake videos. So with that, let's get started and let's look at what GANs are. So GANs are a type of generative models where we try to learn the underlying distribution of from which our data set comes from. We've looked at one generative model already last week in the recitation, and this week in lectures we looked at variational autoencoders. Um, they were trying to do a similar thing. We were trying to uh, create a generative model that for us would take in as input a latent vector and give us give us outputs which are from the same distribution, which come from roughly the same distribution as our training set comes from. Now, GANs are a little different from variational autoencoders, for they have a component called adversarial training, uh, where there are two components in GANs, and they're trying to compete with each other. They're each other's adversaries, and they're trying to beat each other in order to achieve a common goal, which is to create a generative model. And yeah, they're basically the two modules that are competing with each other on neural networks. So what we have in GANs, um, so the first component in GAN is a generator. What it does, it takes in an input vector, which is from a latent space, and it spits out, it generates data. That's what it gives us. Now, from what I feel is like GANs are a more intuitive implementation of how you would train a generative model. So if say I was training a generative model, the generator would generate an image and I would give it some kind of feedback. And that feedback was that, okay, if the generated image seems like to have come from the same distribution that our data was from, I'd say, okay, you did a good job. You've learned how to generate images from that distribution. If it wasn't from that distribution, I'd say no, you need to do better. And I'd want the generator to somehow back propagate my feedback through itself and learn, update its weights, uh, and learn. And that, I mean, it's hard to back propagate my expectations from the generator, but GAN kind of do a similar thing. They have another component in them called a discriminator, whose task it is to tell GANs that, okay, if you're doing a good, if the generator is doing a good job or not. And the feedback from the discriminator is back propagated into the generator, and that's how the generator learns. Now, there's also this component of adversarial training. Now, generator and discriminator, they're both neural networks, and they're adversaries of each other. So what happens here is the generator is a neural network whose task it is to generate images. And the discriminator is a neural network whose task it is to distinguish between two classes of images or two classes of any kind of uh, vector in some sense. One is the actual data set, which we call by the label of real data. Like for our example, we'll be looking at MNIST images. So MNIST, anything that comes from the actual MNIST data set is labeled as real. And then there is another class of generated data, which is generated from the generator. And that comes under the label of fake data or generated data. And the discriminator is basically a binary classifier that distinguishes between generated image or real image. And then it, then it gives the feedback to the generator who then learns from the feedback. Now, as we go ahead, I think my aim at the end of at least the first part of the recitation would be to make it clear how these two networks, both of them, generator and discriminator, they are neural networks, how they're adversaries of each other, how they're competing, and how that competition achieves the task of creating a generative model. So let's begin and see how we train again, and I hope that makes things clear. So let's see what we have at time t equal to 0. We're just beginning training. We have two components. One is a generator. The generator is a neural network. Now, the generator will take in a latent vector from a low dimensional space and generate an image, which is a higher dimensional image. So for the example, I'll show the latent vector is say 100 dimensional, and the generated images are MNIST, so they'll be 784 dimensional. So what kind of a neural network will a generator be? It will be a neural net that takes in 100 dimensional input, and you'll have multiple layers that increase the size of the input so that the output dimension is 784. Now, sorry, I think I have a question here. How do we generate a latent vector? No, so the latent vector is not generated. So the latent vector comes from our chosen distribution. So what we're trying to teach is the generator is how to generate images from our chosen set of latent vectors, or a chosen distribution of latent vectors. Yeah, exactly. It's a random vector from some distribution that we choose, and we are teaching the generator how to create some kind of correspondence between our chosen random vector or chosen distribution to the data set that we want to generate from. Yeah, so the generator is a neural net that takes input, low dimensional vector, generates an image which is higher dimensional. Now, what kind of neural net would a discriminator be? The task of the discriminator is to distinguish between two classes. One class is the real data, which is basically a given training set, which comes under the label of real data. The second class is our generated data, which comes under the label of fake data. And the discriminator is basically a binary classifier. All it does is it classifies these two labels. It's basically a binary classifier between these two classes. So now this is what I have. So what kind of a neural net a discriminator be? It will take in inputs of the size of images, and it will give a 0-1 label to the image. That if it comes from the real data, it should give a real label to the image. If it comes from the fake data, it should give a fake label to the image. So now I want to train a GAN. Which of the two networks should I train first? Anybody has a guess or wants to? The discriminator will receive. So I have a question here. Let's see, Kieran. Let's see what the discriminator will receive. That's what I'll discuss in the next couple of slides. So anybody wants to take a guess which of the two networks, the discriminator or the generator, I train first?
Can you train them at the same time?
Well, we're kind of training them together, but like it kind of goes in some order. So you train one network first, and then using that we train the other.
So the discriminator is required to train the generator. So the discriminator needs to go first because it's providing the loss for the generator, and if it's off, then neither will ever be on, like, correct. right?
Yeah, exactly. You train the discriminator first because that's what, in some sense, is teaching the generator or giving feedback to the generator. But with what training data? Where does the training data for the discriminator come from?
The generator will produce badly formed videos at the beginning, right? Generally, so we could probably guess they're almost always wrong, or I'm not sure.
Yeah.
Yeah.
Sorry, go ahead.
Oh, I'm guessing that at first you won't have a generator technically because you're training this discriminator first. So for the fake data, you're just passing random data or something like that, and then hopefully later on you can use like the features or like the layers in discriminator to train back the generator or something like that.
Yeah, exactly. Or I mean, like in some sense, you could, so you always have a generator, but like at time t equal to 0, you have a garbage generator, but it would still give us something, right? So the discriminator, it's a binary classifier. It has two classes: real data, which by definition is our given data set, and fake data, which by definition is anything that comes out of the generator. So at time t equal to 0, I mean, we have the real data. We always have the real data, which is the training data. And we generate the fake data from the generator. So anything that comes out of the generator is the second class. And so at time t equal to 0, we have a garbage generator, or at any other instance of during training, we have a generator. We generate a set of images or a set of whatever kind of training data we have from the generator, and that makes up the second class of our binary classifier. So we basically use the generator, whatever state the generator currently is in. At time t equal to 0, it's just garbage initialized values. At a later time, it has learned something. We use the generator to generate the second class of our training data. So this is the data that we use to generate to train our discriminator. Now, what's next? We have to train the generator. So we've trained the discriminator once. Now we have to train the generator. But how? Like, what's our training objective here? Like, because if we don't define that, uh, then it's hard to. Uh, I mean, like we need to define a training objective before we start training the generator. So any guesses what our training objective is here when we're training the generator?
You're trying to increase the loss of the discriminator in a sense.
Yeah, that's correct. We're trying. That's exactly correct. What we're trying to do is we want to generate images from the generator such that they are classified incorrectly by the discriminator. That's our objective. The discriminator, let's say it labels the data that comes from the generator as fake. We want the generator to generate images that the discriminator labels as real. So that's basically our training objective here. Yeah, so in some sense, the generator is trying to beat the discriminator here by making it do something incorrect. And the discriminator in the first step was also trying to be a step ahead of the generator. It was trying to classify whatever it did, like whatever images it produced as the images it produced and not the training data. So in summary, what happens while we're training GANs is in the first step, we train the discriminator using the current ability of the generator. And what I mean by using the current ability is that whatever kind of generator we have, we generate a bunch of images from the generator. And that set of images comes under the label of fake data. And we already have our label or our data set for the real data. And we use that to to train the discriminator. In the next step, we train the generator to beat the discriminator. And what the definition of beating is, and what our training objective is, to generate images from the generator that are classified incorrectly by the discriminator. And we just keep on doing that. We keep on doing that. In the first step, the discriminator, in some sense, tries to get a step ahead of the generator by being able to distinguish between anything that's generated from the generator or it comes from the real data. So essentially, if the discriminator is not able to discriminate or distinguish or classify correctly something that comes from the real data distribution and something that comes from the generated distribution or from the generator, then it essentially means that the generator is generating from the same distribution from which our real data comes from. And in the next step, what the generator tries to do is tries to beat the discriminator, who's already one step ahead of the generator. So it's trying to learn from its mistakes there. And both of them are trying to beat each other in order to achieve a common goal of training a generative model, which in this case, in our case, is a GAN. How do we decide to stop the training? Yeah, well, that's one thing to do is that you kind of see if the loss saturates. Another, and in some sense, that's what makes it hard to train GANs. I mean, not the fact that when to stop training, but you're training two different neural networks, one by one, and the training is in some sense unstable, and you're not always likely to converge. And I think it's a very good question. It's a very practical issue that we come into, and Kushal might show you an example of such things happening. But yeah, that's a good question, which we'll get into in this recitation. But that's what's happening in a GAN. We're training the two networks in a loop, one by one, with the objective of at every step, one network is trying to beat the other. And our aim is to create a generative model. So that was a quick introduction or quick introduction to training GANs. Next, I'll be showing you the code, which hopefully will make things even more clear. But at this stage, does anyone have any questions?
So for the example you gave of that video, the latent space was some embedding of the audio there?
The example of the video. No, well, I think that was trained using a different kind of GAN. Kushal, correct me if I'm wrong, but I would assume there to be both an audio and video. Kushal, was it something related to style transfer in that video that I showed?
I mean, I wouldn't guess if it was style transfer. I'm not sure about that, but it certainly does not just take into account the audio or the video. It takes into account both of them. It's some sort of a multimodal learning going on there. So I would assume, I mean, I'm not really sure exactly what the architecture was, but then it's for sure, I mean, it's using both the video and the audio, like simultaneously embedding them into a latent space.
Yeah, that's
I
what
mean, as you'll
thought.
also look at like a couple of other things that go around. I mean, so there's certain things that are called conditional GANs. I guess you will learn more about them during the lecture that Ben takes. But then in a conditional GAN, you're essentially training an audio, and let's say you're basically have two variables instead of one, and you're simultaneously training a joint distribution of variable one and variable two. And once you train this joint distribution, you specify one of those variables and then try to vary the other. So I would assume that this was probably something similar to that, wherein you were training you train multiple videos where you probably trained like multiple things where you had videos and audios, and then you fixed the video and try to switch between the audio such that you got that kind of an impact. I guess style GANs probably also work in a similar, I'm not really sure, but yeah, I would assume that's something closer to a conditional GAN than a vanilla GAN.
Okay, so let's look at the code. I have the slides here, so we'll try to create a one-to-one correspondence from what we saw in the slides and what's there in the code. So we start with the generator network. It's just a neural net that takes in a latent dimensional input and outputs a generated data, which is dimension of our image in this case. So this is my very simple generator. The input it takes is the latent vector dimension, and the output it gives out is the output image dimension. So they're kind of defined here. The input that goes into the GAN is the latent vector dimension. The output that comes out of so not the GAN but the generator is the MNIST dimension. And it's like a very simple feed-forward network. It increases the size of the input at every step. Now, the discriminator. The discriminator is another neural net, which is basically a binary classifier. So, and what it takes as input is our images. So, the input dimension is the dimension of the MNIST data in our case. It's the input image dimension, and the output dimension is just 1 because it is doing binary classification. Yeah, so and it's just a bunch of linear layers here that are reducing the size of the input, and finally the output size is just 1, where you're giving a 0 or 1 as an output. So how to train a GAN? In summary, this is our training loop, where first we train the discriminator, and then we train the generator. So if you look at this, so we have different epochs, and for each batch in an epoch, we first train the discriminator, and then we train a generator. Now let's look at the different training loops. So this is where kind of the magic happens. The neural nets are usual binary classifier, and generator is also pretty simple here. So which network do we train first? The discriminator, and we train it using the training data that is like the data from the fake class is generated from the generator. So it's kind of shown here. We have 2 classes of data. The first is the data that comes under the class real, and what it basically has is the MNIST data set. So X underscore real is the MNIST images. Y underscore real, that's just the set of all ones. So I've labeled anything that is from the MNIST data, it's labeled as 1. And it goes, the images go in the discriminator, and the loss is calculated with the label 1. Now when we're training the discriminator with the fake images, anything that comes out of the generator. So sorry, this is the generator. So now what goes in is the latent vector of the dimension of Z, and that's what goes in. Z goes in the generator, and what comes out is the output image. And the label, so this is basically the set of images that will go into the discriminator under the label of fake. And the label for fake is zeros here. It's all zeros. So like in the case of real images, it was all ones. Now it's all zeros here. And now the loss is calculated against the output of the discriminator and a bunch of zeros. which is the label we give to fake images. And then the discriminator loss is added, and we do a backward pass with that.
Do we not have to shuffle the real and fake together? We can do it separate like that, where you do all real and then all fake.
Yeah, I mean, you could
Make a
shuffle
difference?
them together as well. So I just kept them separate so that it's like just abundantly clear that
Okay.
we're doing these two things. Yeah, yeah. Okay, so next we have the generator, where our training objective is to generate images that the discriminator classifies incorrectly. So what's happening here is, so this is the generator code. What goes into the generator is a latent vector. So it's a random vector you see here in the latent vector dimension. Now the generator generates a bunch of images using that latent vector. Now and then the generated images are sent into the discriminator, but we want the discriminator to classify these images incorrectly, which means that the job of the discriminator is to give all zeros for these images, but the generator wants them to be classified as all ones. So now you can see that the labels for the generated images is all ones, but these labels are the target labels from, so these labels are the target labels from what classification comes out of the discriminator using the images that were generated by the generator. So this is how we incorporate the training objective, that the generator needs so the generator aims to get a misclassification from the discriminator. So because ideally, if the discriminator was performing as it should classify all these images that were coming from the generator as zeros, but the generator wants them to be classified as a bunch of ones. And then the loss is calculated, and you kind of step back propagate, and that's it. So that's how a generator is trained. And then you kind of keep doing that until you have some, I don't have a plot here, I think, but you have some semblance of convergence. And yeah, that's basically it. And I can show you the results of the scan. So these are a set of images for MNIST and fashion MNIST that were generated from just from the GAN I showed you. So these are different epochs. The images are kind of getting better. This is how the generated images look like at epoch 20. So they kind of look bad. They keep getting better with as the GAN trains. Similarly for the fashion MNIST, these are the generated images, like 100 images altogether. Kind of get better as the GAN trains. So yeah, that's basically it. I hope I was able to like make that point come across of how the two networks are adversaries of each other, and how to train a GAN. So at this point I'll finish. So if anybody has any questions from what we covered as of now, feel free to ask. Okay, cool. So good. Kushal takes over from here.
Let me share my screen. Okay, so for this next part of the GAN recitation, we're going to look at the easier part of GAN, which is how not to train a GAN or what can go wrong when you're training a GAN. All right. So as I guess Akshat already mentioned, everything, so the entire purpose of having this recitation was so that you get a sense of what GANs are, how they look like, and what they can do in practice and what their code looks like, so that when you attend Ben's lecture next week, you have some sense of what's going on. And whenever he talks about the theoretical details of GANs and also touches upon different kinds of architectures, you have a better sense of what's going on. And I would honestly suggest that once you're done with the lecture, then you come back to these notebooks and then try to experiment with them if you're interested. I guess that is going to give you a better insight into what GANs are, how they work, and also the kind of issues that one faces, especially the issues bit, I guess. All right. So here's what we are going to do for this part. I'm going to primarily compare GANs with VAEs at the beginning, given the fact that both are generative networks. So it's only fair to compare them. But as some of you might have realized, they aren't really, there isn't any one-to-one correspondence, because if like some of you might have noticed that there is no encoding in a vanilla GAN. Like there is no way for you to take a real image and take that image and move into the latent space from there. You can move from the latent, you can sample something random from the latent space and move that to the output space using the generator, but there wasn't anything uh, like an encoder in this GAN setup that Akshat spoke of, which can take your real data and take it to the latent space, at least not in the vanilla GAN. So even though they are trying to do the same thing and trying to model the probability distribution of a given data set, there's this slight difference between the two, because at the end of the day, we are just going to compare how well network one does as far as distribution of these images concerned with respect to distribution two. But I believe the ability to move from the data set to the encoding space is also something really powerful. And for that purpose, I have chosen like a couple of GAN, or rather GAN related architectures that preserve this encoder decoder structure, so that we can have a better comparison between the two, rather than comparing just the generators of a VAE with that of a GAN. Now, before we move into these different architectures and talk about the issues that are there as far as training, I would just give you a quick couple of points as to where GANs and VAEs differ. So one thing which is often cited as an important distinction between GANs and VAEs is the ability of GANs to produce extremely crisp and sharp images or data set that very closely resembles that. I mean, because most of the work is done in uh, images space, so I'll probably use the example of an image whenever I'm talking about the data set, because that's a lot easier. So GANs produce these very sharp and crisp images, whereas when you compare images that are generated by VAEs, they are a lot blurry. So that is something that's very important, and that takes things into the favor of GANs. But the issue with GANs is it is extremely hard to train, like extremely hard to train. And this is still an ongoing thing where people are trying to figure out ways in which one can improve the stability of GANs training. On the other hand, you have VAEs that have some really nice underlying mathematical foundation, coming from this non-linear Gaussian model that I guess Bhiksha spoke of during the lectures. So you have these non-linear Gaussian models that have some really nice maths supporting them. And then from there, you move on to this VAE space. So, I mean, there's a lot of theory behind it. As far as GANs is concerned, a lot of this is, I would say, empirical compared to the theory that supports VAEs. So, those are probably like important distinctions. Apart from that, obviously with VAEs, you have this encoder, which is, I believe, way more useful than a discriminator in a GAN, because once your training for a GAN is complete, you throw away the discriminator and it actually serves no other purpose. But I believe in a VAE, having the encoder is an important thing in my personal opinion, as with the encoder you can transform your data set into the latent space, and if your task is something else, then you can let's say, so actually, how about we just move on, and I'm going to talk about the specific topic. The specific point that I wanted to make would be clearer when we talk about this special VAE architecture that I've implemented for the purpose of this recitation. So, yep. So everything's in. The notebook uses something called Ignite in order to structure the code. So if you're not sure what's going on, you might want to just look at that. Yeah. So this is a data set that we are going to work with. So we have the smiley data set. The red, the green, and the blue, they are, I mean, this is an unsupervised learning task. So these labels, these so-called labels that I have plotted in front of you are just for the sake of understanding that there are primarily these three places where the data exists, so that it's easier for us to visualize what happens during reconstruction. Because it wouldn't make a lot of sense if the GAN or the VAE is plotting these red points here and the blue points here. So that's not something that we want. We want some kind of structure to inherent structure that exists in the data set to be preserved while it is generating the data set, right? So if let's say if in the reconstruction space we find that this specific part has both red, green, and blue, and this has red, green, and blue, and this also has red, green, and blue, then that sort of isn't that great generation. Like that generative model isn't that great, right? So we would want to see some sort of separation between these colors ideally. And that's important to keep in mind, that all that we're speaking of here is something that should happen in an ideal setting. So that's the data set that we're going to work with. We generate a bunch of, we generate the synthetic data right here. And then let's try to use a VAE in order to learn the distribution for that data set. So this is the code for the VAE. We'll touch upon this in a bit. Let me just show you how the results look like. So we begin our VAE training with this data set. I guess you touched upon the VAE data, like the VAE training methodology and the VAE architecture last time, so I won't go into too much detail as far as that's concerned. So these are the plots, the trainings, like what happens during the training. So more often than not, this is what you'll see or observe whenever you're training a VAE. Your reconstruction loss, which is primarily the purple line and the yellowish line, this bit goes down, and your KL divergence goes up, and your effective loss, which is the sum of the two in a vanilla VAE, also kind of goes down, right? So this is what you'll generally find. Yep. And this kind of, and in order to interpret this, like what's happening here, what essentially happens is that the Gaussian assumption that you make on the latent space is kind of a regularization, or it in a way limits the capacity of the latent space to express the data set. Because at the end of the day, if we were to let it loose, then the latent space can learn any random distribution, and our end goal of coming up with something that can generate the data from Gaussian noise gets defeated. So we want to maintain that constraint on the latent space, but we don't want that constraint to be so strict such that no learning takes place. So this is what essentially happens. So initially, let's assume that without learning, the unlearned embeddings. So let's say you initialized your encoder and you mapped your data set onto onto the latent space. So initially, because there was no learning, so it kind of maps everything that is random inherently and probably looks very similar to a Gaussian, and therefore the KL divergence is pretty low. But as it starts learning, this loss goes up because it is allowing the latent space to learn something, and given that it is not able to constrain everything into a Gaussian, this loss kind of rises. But what you gain out of this is a better reconstruction, right? So the information is kind of getting encoded into the latent space and the decoder simultaneously, on how to generate the samples. So this is how generally a VAE training schedule looks like. Now let's look at the results. Right. So this is the latent space and this is the reconstruction space. They look kind of similar because the latent space that I'm using is also two-dimensional, and the space, the outer or the output space was also two-dimensional. So you might find them to be similar. Actually, they are pretty similar, but that's not always the case. So, don't generalize based on what you see for this specific data set and this specific VAE schedule that we are going to follow. So this is how things look at the beginning, and that's why, given the fact that this uh, the latent space right now looks very similar to a Gaussian, kind of explains why the KL divergence initially is so low and why the reconstruction loss is so high, because this does not resemble anything like what our data set was. But then as we go on and as we train, a separation kind of takes place. These are, so this epoch 6, epoch 11, epoch 11. So, a lot of stuff happened in the middle, but I plotted just every fifth epoch. So the separation kind of takes place, and the blues and the red, the blue is separated from the green and the red, and I guess that's primarily because learning red and green, because of symmetry, I guess, was much harder. Blue was significantly different in terms of how it was compared to red and green. So I guess that's why this separation takes place first. And you can see the separation happening both in the latent space and the reconstruction space. Um, so what's happening here? The fact that the encoder is now mapping these blues to this specific part of the latent space and the green and the red to this specific part of the latent space. It's very easy for the decoder to now guess what it needs to construct based on where the noise is, like what part or what the mean of the noise is. So based on that, it's able to do this reconstruction. But it's still obviously not the greatest generative model that we have trained right here, given the fact that the red and the green are still merged or squashed together. But I trained this for like a brief period of time, I guess like 20 epochs or so, something like that. Yeah, I guess it's for 30 epochs. Yep. So that's what it essentially looks like. It tries to morph into a smiley as far as this is concerned, but that's the best it's able to do. So there are a lot of so given the training that I'm using here is not extremely or highly tuned, as I'm not using a scheduler of any sort, and I guess the hyperparameter training for the learning rate and other things are also not something that I paid a lot of attention towards. So I guess with those, you might be able to see a better separation. Also, once again, the architecture is also something that's extremely important here. I used a very vanilla architecture, used simple blocks of layers in order to construct this VAE, and therefore that's another reason why the separation isn't that great. But I guess you could alleviate all of those by working out a better architecture or a better training schedule. Now, what's important here is to realize that when I was training this entire VAE bit, it almost always got stuck somewhere around this 1.8 mark as far as the training loss. So it would just remain at 1.8 forever, like even for 100 epochs or so. And that's also kind of reflects the inherent issues that sometimes may also creep in in the VAE setup as well. So Gans is worse. So in order to alleviate this, there's a special VAE architecture that I employed here. It's special in theory, but in terms of how it's actually implemented, it's extremely easy. So this is essentially called beta VAE, and a beta VAE essentially reweighs the two terms that you have in the objective function. So you have the reconstruction loss term, and then you have the KL divergence term. The beta VAE, instead of just adding them like in a one, like just weighing them one and one and adding them together and then optimizing that objective, beta VAE essentially reweighs them. So if you're looking for some mathematical justification as to why that is great and why that happens, you wouldn't find much in there. This is very empirical. And if you look at the original paper, they give you a number of hypotheses as to why that's happening. But it helps a lot. So it helped in this particular case where I was able to use a beta beta value of 0.8, and I multiplied that beta with the KL loss term right here. So what this essentially does, it just says that I'm not really concerned about the KL divergence loss much. Please focus on the reconstruction loss. So it kind of nudges the VAE optimization towards creating a better reconstruction loss than a KL divergence loss. So, and apart from that, there are other properties of a beta VAE which you can probably look at, go through when you go through the paper, and if you go through the paper. But there are things such as the fact that this latent space, I guess that this is one specific manifestation, like the fact that you're able to see this clear separation between the two, and the fact that it resembles the reconstruction space so much, I guess is a artifact of us using a beta VAE here rather than a vanilla VAE. So the fact that we are using so what a beta VAE essentially does, like as far as empirical results go and the hypothesis of the authors go, the latent space, every dimension in the latent space starts becoming more meaningful, right? Originally, if you train a vanilla VAE, then there is no meaning associated with a specific dimension. You could just move around and you get different kind of samples. Well, that's good. But then what if certain dimensions represented certain things, right? For instance, let's say if we were to talk about faces, and you generated a beta VAE with faces, then one of the dimension might represent color of your hair. One of the dimensions might represent, how big your eyes are, something of that sort. So what the power that you get when you have something like a beta VAE, or rather when you have something like informative latent dimensions, is that you have explicit control over what kind of an image that you want to generate. So you can generate and one of the dimensions could represent age. So for instance, if that were the case, and you encoded, or you took your image, you passed it through the encoder, and you got the latent space representation of your image or your face, and now you want to look at how would you look 20 years down the line, or how would an older version of you look like, then you essentially just take that latent space representation and move along the dimension that represents age. And as you move along that specific dimension, you'll find that your face becomes older while all the other characteristics kind of are preserved. So that's what's great about having a latent space representation which is meaningful. Now, you don't really get a lot of control over which dimension represents what. That just happens on its own. Like the beta VAE prioritizes features which are more important for the reconstruction than others. So for instance, a simple example would be, or something that you'll find in the paper is an example of that of a Gaussian ball. So they train the data set. So the data set consists of a lot of Gaussian balls. So it's basically a white ball on a black surface. And the data set has many representations of this, wherein the specific position of the ball is different, the size of the ball is different. So that's essentially the data set. And what you'll realize is that certain dimensions start corresponding to the x-axis, or the x-axis of where the ball lies. Certain dimension in the latent space start corresponding to the y-axis, y position, the vertical positioning or the horizontal positioning. And one of them starts corresponding to the size of the Gaussian ball. So, and that becomes apparent, like it's experimental, you'll have to see like which dimension corresponds to what. But that is something that you'll observe with a beta VAE. And I guess that is what you see here in some sense. The fact that the beta VAE prioritizes this positioning of the data along the vertical axis. And that's why you see the blue lines are being mapped here and the red and green are at the top. So that now if you take a point and map it to this latent space and move along the y-axis, then you would essentially move from being a red or a green dot to a blue dot, or from a blue dot to a red or green dot. So this dimension now, the y-axis, is meaningful. So yeah, so that was a long-winded explanation or a description of what a beta VAE is. And the paper is very simple, very approachable. I would highly recommend that you go through it. It's awesome. Yeah, and they have much more complicated, much more complex data sets that they work on, and then show how they are able to learn a meaningful representation in the latent space. So that's how our VAE or the beta VAE looks like. With this, we move on to something that's called an adversarial autoencoder. So now what an adversarial autoencoder is. So adversarial autoencoder is essentially an autoencoder. All that's different here is the fact that your latent space, or the KL divergence term that you had in your vanilla autoencoder or your VAEs, is now replaced with something else. Because if you remember, your VAEs are essentially trying to optimize a lower bound, which is what we call as an elbow. So it's always trying to optimize a lower bound. What we try to do in practice, once again, there isn't a lot of theoretical justification that you'll find here. I mean, you might find certain theoretical justifications in very specific settings, but this is not as generic as a VAE in terms of its mathematical foundation. But what this essentially tries to do is that it tries to optimize something better than just a lower bound, and hopes to achieve better results compared to a VAE. And what we essentially try to do is replace the KL divergence term in your loss function with something that resembles a GAN. So we train a discriminator, and now you have your encoder, you have your decoder, you have your data set that goes through the encoder, gets mapped to the latent space, passes through the decoder, and the reconstruction comes out, right? So that's what your VAE looks like. Now, instead of having a KL divergence term, whatever you map from a real data set onto the latent space, that distribution is now considered a fake Gaussian distribution, right? Because you're trying to emulate a Gaussian distribution, but in the absence of a KL divergence like penalty regularization, it could be anything. So we wanted to at least simulate a Gaussian distribution, or at least try to look like a Gaussian distribution. And in order to do so, we take that distribution that is being mapped onto the latent space, pass it through a discriminator along with a real Gaussian, right? A real Gaussian generated data set. So now the discriminator tries to distinguish between the data set that is being generated by a real Gaussian and the data set that is being mapped onto the latent space, right? So if a discriminator does a good job, it would be able to figure out, that this data, the embedding data space, the embedding distribution that you have is fake, does not look like a Gaussian, and then your VAE or your encoder rather would face a challenge where it would need to do something else in order to see to it that it maps the real data onto the latent space such that it resembles a Gaussian. So instead of a KL divergence term, you have this discriminator that's trying to identify whether the data set you're passing in is fake or real, and whatever the output is being used as a penalty instead of a KL divergence. And we hope that this does well. So that's essentially what a adversarial autoencoder does. So to summarize, it essentially replaces your KL divergence term. It replaces your KL divergence term with something that utilizes a discriminator in order to penalize the distribution in the latent space if it diverges from that of a Gaussian, right? All right. So let's look at the results, how it fares. Once again, the training schedule that we have is very vanilla, not very tuned, even the architecture for that matter. And therefore, I just trained it for like 10 epochs or something. And this is what it looks like. What these loss terms mean, I'll go through them like in a bit. But let's look at the results, right? So this is what the results look like, right? The results look very similar to that of what we got from the VAE. So initially, this is what the initial thing looks like after epoch 1. I'm sure epoch 0 has everything that's squashed one, like the red and the green overlapping with the blue. But as the AAE or the adversarial autoencoder trains, there is a separation again that we observe here. What's interesting here is to look at what's happening here on the latent space. While again there is a separation in the latent space and the blues and the greens are separate, you'll realize that there is no correspondence between the y-axis in the latent space. Like, there is correlation, but it isn't exactly trying to learn the y-axis positioning of the data set in the latent space, right? There is some correlation, of course, but then it isn't exactly the same. So that's where beta VAEs in a way shine, the fact that they are able to do a much better job as far as that's concerned. So yeah, there's that. So this is what the results look like. In terms of how this autoencoder looks like, let me just go through that as well. Right. So this is the training loop or a training step. And what essentially happens, right, let me just also give a brief description as to what's happening here. So you have an encoder network, you have a decoder network, and you have a discriminator. So this is right here, it's different from a GAN, because for GAN you have just one network and a discriminator, a generator and a discriminator. Here we have a separate encoder and a separate decoder, and you have these bunch of optimizers. One optimizer corresponding to the encoder, one optimizer corresponding to the decoder. You have one optimizer corresponding to the encoder when we're trying to regularize the distribution in the latent space. So that's a separate encoder. And then you have a optimizer for the discriminator. So this in itself should in some way reflect the kind of issues that we're going to face when you try to train a GAN. So we have like these bunch of optimizers, at least two optimizers, even in a vanilla GAN compared to that of a VAE. VAE just has like a one optimizer. So you're good. You can just train the learning schedule for that single optimizer, tune the learning rate, tune the weight decay, whatever you want, and you're good. Here you have like four of these. How do you decide which one, like what to use for these various optimizers? Which optimizer to use? That also becomes a question. Because an important issue with GANs is that if you overtrain a discriminator, like if your discriminator becomes really, really good and your generator isn't that good, then you're going to face a situation where the results from discriminator are going to saturate. So because it's a binary classification, a sigmoid is a good example. So let's say all the fakes lie here and all the reals lie here. And if the discriminator is really good, then it's going to turn into a step function. And what's bad about a step function is the fact that now we don't have any gradients to work with, and the generator is unable to decide how should it go ahead and modify itself such that it's able to do a better job at faking, and that kind of defeats the purpose. So our generator isn't able to learn, and everything sort of kind of stops there. On the other hand, if the discriminator is undertrained and isn't doing a great job as far as classifying the generator from a discriminator, that does not always mean that your generative model is doing great. That can also mean that your discriminator is really bad and has no idea what's going on, and therefore cannot provide any valuable feedback to the generator based on which the generator can learn and modify its distribution. So the generated distribution can be very different from that of a Gaussian, and still your discriminator is unable to identify which one is which. And that isn't a good place to be in, right? Because that kind of defeats the purpose or our end goal. So you have to be careful about how much you train your discriminator and how much you train your generator. So the setup that Akshat touched upon was a very simple one, where you train a discriminator first, then train the generator, train the discriminator again, then train the generator. And but then, is that what you should necessarily do? Should you try to train your generator for multiple epochs before training the discriminator once, or should be the other way around? Should you train the discriminator for, let's say, 3 or 4 iterations before you train your generator? Like, what should be a good balance between the two? So a lot of people try different things, and that kind of reflects the inherent complexity in training a GAN. Along with this, an important fact that I would like to touch upon here is the objective function that you're essentially training, or the objective or the vanilla formulation of a GAN that Akshat touched upon in the initial lecture, that also isn't very stable. So if you did everything well and you started training your GAN, it might still be extremely unstable the entire training, because the training in a vanilla formulation is, so the objective function that you get for the generator is actually discontinuous, and because of that your training can be extremely unstable. So in order to alleviate that, people came up with different objective functions, or rather different formulations for the GAN objective, and one of those is called the Wasserstein distance, or the Wasserstein GAN. And that is something that's extremely popular, and kind of alleviates this issue with stability to a great extent. But in the original formulation of for the Wasserstein GAN, there are a bunch of issues there too. How Wasserstein GANs work and what kind of issues there are, I guess Ben is going to cover all of those things in a lot of detail during the lecture, so I wouldn't go into a lot of detail as far as that's concerned. But I'll just say that the original formulation for WGANs is also not that great. It does a poor job in terms of learning complex functions, and it also does a poor job. And also, if you go ahead with the original formulation, you'll find issues such as exploding gradients or vanishing gradients, things that I believe you guys are intimately familiar with right now. So in order to alleviate that, another modification on WGANs came up, which is called WGAN GP, or WGANs gradient penalty. So it tries to impose similar constraints as that of a WGAN, but so WGAN essentially use something called gradient clipping, or rather weight clipping, but the WGAN GP, instead of weight clipping, tries to add a penalization term to the objective function, and claims, and actually rather shows that it can provide a much more stable training compared to that of the original formulation for WGANs. And this is the magic term for the WGANs, like the gradient penalty term that I just spoke of. So this is where the gradient penalty is being calculated. I believe you can go through, once you go through Ben's lecture, you might want to come back here and go through what this function is doing, and maybe experiment with this. Also, the formulations change slightly as far as the loss function is concerned. So let me just quickly show you where that is. Yep, this is the evaluator. So this is the W loss that I was talking about. If you realize, I have the fake predictions and I have the real predictions, and instead of passing them through a log function and then kind of combine them, I am not doing so. I'm just taking a mean straight up, and this is part of the WGAN GP formulation. And then there's obviously this gradient penalty, and once that's done, then you go ahead and perform your backward, and so on and so forth. So so that's about AAEs. AAEs look similar to VAEs, but the KL divergence term is replaced with a GAN-like setting to constrain the distribution in the embedding space or the latent space. And we have a further modification here on top of that, which utilizes the WGAN GP penalization, so that training is more stable. Also, like there is another hyperparameter that gets introduced as a result, which is this lambda function. This lambda function is multiplied with the gradient penalty term that I spoke of. So this again becomes something that you might need to tune. But as per the original paper, for a lot of the data sets that they work with, lambda of 10 worked really well. So yeah, but you might want to be careful when you're working with toy data sets. You might want to tune that as well. So we just saw how complex everything became when as compared to that of a VAE, or rather a vanilla GAN as well. We have 4 optimizers. Each optimizer can have its own training schedule. We also have this issue of how many times do we want to train a GAN before train a discriminator before we train a generator, or how many times do we want to train a generator before we train a discriminator, things of that sort. So those are the issues as far as a GAN setup is concerned. Again, the red and the yellow or the orange line that you see here correspond to the W loss, or the Vassicine loss that I just showed, and the other bits are the reconstruction losses for an AAE. With that, I'll just quickly go through the BiGAN part. So BiGAN is another GAN architecture, which again preserves this encoder-decoder setup, so that we can compare apples to apples. And what this essentially tries to do is that its architecture is very similar to something that we just discussed, like during Akshat's lecture, right? Something that came up, which was called the conditional GANs, where you try to simultaneously learn a joint probability distribution between 2 different variables. I guess that was what was happening in the video that was showed there, where you had video and audio, 2 different variables, but we're learning a joint distribution between them. Here is what we do in a BiGAN. In a BiGAN, we take the original data set and we take the latent space encoding for this original data set. How do we get that? We have an encoder, we pass our data set through the encoder, and we get the encoding. So we have the original data set and the encoding, and now together they form like one set of data. On the other hand, we randomly sample from a Gaussian and call that the fake encoding, and pass it through a generator, generate fake data set, and together this fake data and fake encoding form another data set. So now you have fake encoding, fake data set, and you have real data and real encoding. Pass this through a discriminator and see if your discriminator can distinguish between the two. So from this point on, the setup is similar to that of a vanilla GAN. Your discriminator is trying to distinguish between this joint distribution of the fake data, fake encoding, and real data, real encoding. And while your generator is trying to train in a form in a fashion such that it's able to emulate that closely. And that's it. That's how BiGANs is supposed to work. Again, BiGANs are the easiest as far as training is concerned, but they are probably simpler as compared to AAEs, because fortunately now we have just 2 optimizers compared to 1. Yep. And here too, I've tried to implement a WGAN GP penalization instead of a vanilla GAN formulation. But then this has its own specific issues that you could probably go through when you're done with Ben's lecture, as then it might be more helpful and insightful. But let me just show you how bad a training can look like. So this is how the training schedule looked. The W losses and the G losses, like, once again, forget about what these mean, but you can just see that there appears to be nothing going on right here. And this is what you get as far as your latent space and your reconstruction space looks like. Things just are random. Saying that these are random is an understatement. These just moving around in a very unconstrained fashion. And these are the kind of issues that you'll face when you try to train a GAN. So I guess that was it from my side. I think, again, I would reiterate that you might want to revisit these notebooks once you go through Ben's lecture, as you'll have a much better theoretical foundation regarding what GANs are, how different kind of GAN architectures look like, and what are the issues with training a GAN, and what are probably few things that you can do in order to make your life easier if you want to train a GAN. So, are there any questions that I can answer at this point? I mean, unmute yourself. I'm not sure if I have access to the chat. I don't think I do. All right. Yeah, I don't think there's anything on the chat either. So, questions? No questions.
Will
All
we
right.
ever use this in our homework? I haven't looked at part talk yet. I'm
That's a
just
good.
like,
That's a very good question. Are we going to use this in the homeworks? I guess fortunately or unfortunately, you won't have this as part of your homework. I mean, I personally would have loved if there was a bit of VAE and GANs in my homework, but then you guys won't. Maybe people, I guess not maybe, but for sure, people are going to take this course next semester are going to have this as part of their homeworks. So yeah,
okay.
not for you guys.
Thank you.
Yep. All right. I guess that's it. Thanks everyone for joining. If you have more questions, feel free to reach out to us, come to H or whatever. Yep. All right. Actually, do you have anything else to add before I end the meeting?
No, nothing. Thank you, guys.
All right.
Thank you.
See you. All the best for homework for P2. And if you guys haven't started working on homework for P2, then you are in trouble. I'm not sure if you're gonna like cross the thresholds. All right. Bye.